Hey class, in a different spot. Today I'm just at my house, working from home a little bit. So we're going to move into our last lecture for exam 2. So this is the last of the material that will be covered on exam 2. And then I'll also post an exam 2 review that kind of outlines exactly what you need to know for the test, and give you some more information about it. So, all right, let's get going on this. All right, so hopefully in this lecture we can kind of tie everything together that we've been learning so far. Exam 2 really is can be largely summarized by one topic, which is stoichiometry. Those are also the gas laws that we learned too, and then like molecular shapes and stuff like that. So I feel like this exam might be a little more, I don't know, cohesive maybe is the right word. The first one was kind of random ideas, but anyway, go ahead and pause the video and try and do this question from the previous lecture. Okay, here we go. So quiz says you have a reaction that generates 275 milliliters of nitrogen dioxide at 125 Celsius and 2.5 atmospheres. How many moles of NO2 gas is this? So one thing people sometimes struggle with gas laws and gas equations is knowing which one to use. And my answer to that is kind of what it's been previously, and that is to start writing things down. So for example, if you think, well, let's just start writing things down on here. So we have 275 mils, so that's a volume. That's 275 milliliters. And we have a temperature, which is 125 Celsius, which would be, what, 398 Kelvin? Okay. And then our pressure is 2.5 atmospheres. And then it's asking for moles, right? So just writing out what you have really tells you what you can do. For example, in this question, we just have one volume, one temperature, one pressure, and we're asked for a number of moles. If a question gives you like 2 different volumes and 2 different temperatures or something, then you know you're going to be using like Boyle's law or Charles' law or something like that. Because in those laws, right, like Boyle's law, for example, we have 2 pressures and we have 2 volumes, right? So we wouldn't be able to use any of those here because we only have 1 volume, 1 temperature, 1 pressure, and we're looking for 1 amount of moles. And so when it's just one of certain things, then that would tell you that you're using the ideal gas law, because the ideal gas law doesn't have multiple volume or more than 1 volume or more than 1 pressure or something like that. Okay, so that tells us that we need to use this equation, and we're trying to solve for n. So we can say n equals PV over RT. We have P, we have V, we have T, and we have R. Okay, so we can just plug all the numbers in and put it in our calculator. Last thing you want to check before plugging in the numbers is units. So R kind of reminds you what units you need. We need liters, and here we have milliliters. So we need to convert this to liters, 0.275 liters. We need atmospheres, which we have. We need Kelvin, which we have. And moles is what our answer is going to be in, okay? So just run through the calculations and get your answer. So again, probably the biggest part is like figuring out which equation to use and then just setting it up. As long as you're okay putting numbers into your calculator, at that point you should get the answer right. Okay. All right. So we're gonna talk a little bit more about mixing gas laws and stoichiometry now. And I hope you can see how this is very similar to what we've done like a million times with the mass calculations and limiting reactants and stuff. So this is my final roadmap, okay, that I'm probably going to post. And this is the more complete one. Before we looked, what we've done mostly is gone from grams of A to moles of A to moles of B and then to grams of B, right? We've done this. This is the mass calculation that we just did all the time. But there are other ways we can get to moles. So depending on what we're starting with. If we start with molecules, we use Avogadro's number. Right? If we start with grams, we use molar mass. And we could also start with volume. And then there's basically, that's the rest of this. And there's three different scenarios. One is if you have a solid and a liquid, solid or a liquid, you're going to use the density to convert from volume to grams. And then from there, you can convert from grams to moles. If you have a gas, so either one of these two, you'll have the option of, if the reaction's at standard temperature and pressure, you can use 22.4 liters per mole. That's just the standard for gas at standard temperature and pressure. If it's not at standard temperature and pressure, then you're going to use PV equals nRT, right? You're going to rearrange it for N equals PV over RT, and you can solve for moles, and that gets you from volume to moles of whatever it is. And then it's the same as true on the other side. You notice that the only way to cross between A and B is your molar ratio, right? And this comes from the chemical equation. This is the only way. You can't, I guess I shouldn't say it's the only way. Well, okay, sorry, I guess this isn't totally complete. Add this little part in. Volume, you can convert, right, from volume straight over to volume of A straight over to volume of B under certain conditions, and we talked about this in the last one. So this is if pressure and temperature are constant, okay, that's when you can convert. So if pressure and temperature are constant, then you have Avogadro's law, right? V1 over N1 equals V2 over N2. So if P and T are constant, the molar ratio, we talked about, like, derived the whole thing in the last lecture if you missed it, but the molar ratio is equal to the volume ratio. Okay, we talked about that, but only under certain conditions. Okay, for the midterm review, I'll probably add in this other arrow to explain it better. Okay, that should be the complete picture there. So we'll kind of reference this as we work through some problems. And if you struggle with these problems, I would highly recommend memorizing this map. I'd recommend memorizing this map. It can be super useful. You can't write this down and take it with you while you take the test, but you can have scratch paper on the test. So you could start the test with no notes, right? And then if you had this in your head, you could write it down on your scratch paper, and then you could use it that way. But you would need to memorize it first. Okay. Go ahead and try this example, and you're welcome to reference the map from the last slide if you need to. Okay, so let's go ahead and work through this. So first of all, usually if numbers are given, the equation's balanced, but just double checking. We have 4 nitrogens on the left, 4 on the right. We have 8 plus 6 is 14 oxygens on the left, 14 on the right, and 12 hydrogens on the left and 12 on the right. So we're good, we're balanced. And the question says, how many grams of water are consumed when producing 1.3 liters of ammonia at 2.5 atmospheres and 85 degrees Celsius. Okay, so we need to convert from, we have a volume of gas, okay, ammonia is a gas we have here, so this is going to be our A. This is the information we have. Even though we're moving backwards, it's still considered A because that's what we're starting with, and then water is going to be our B, okay? So we're going from volume of A, our volume is 1.5 liters, over to grams of B, grams of water. Okay, so if we look at the previous slide, and this tells us that we're at 2.5 atmospheres and 85 degrees Celsius, which is not standard temperature and pressure. Okay, so we have the volume of a gas not at standard temperature and pressure. So here we are. And we need to get over to grams of B. Okay, so to do that, we're going to come along this arrow, come across here, and come down here, right? Okay, so first step is going to be converting from volume of A to moles of A, and we're going to use the ideal gas law to do that. Then use the molar ratio to convert from moles of A to moles of B, and then use the molar mass to go from moles of B to grams of B. Okay, so there's our plan. Convert pressure, volume's kind of, I say volume of A, so volume using the pressure and temperature, convert it into moles of ammonia. Convert moles of ammonia into moles of water using the mole ratio, right? And then convert moles of water into grams using the molar mass. So that's just mapped out right here. Okay. So for the moles of ammonia, we're going to use PV over RT. Plug all the values in. This is given to us in liters, atmospheres. So the only thing we needed to convert here is convert from Celsius to Kelvin. So you have 358 Kelvin is equal to 85 degrees Celsius. And this pops out the moles of ammonia. So now we can take the moles of ammonia and convert from moles of ammonia to moles of water using the ratio, right? We have 4 moles of ammonia for every 6 moles of water. Molar mass converts from moles of water to grams of water, and then our answer comes out there. So hopefully you can see how that map really helps. If you don't like the map, that's fine. Do what you're comfortable with, but anyway, hopefully it's helpful. Okay, let's try another problem. Go ahead and pause it and try this one on your own. All right, so the question says, what volume of hydrogen gas is released when 8.25 grams of magnesium reacts with excess hydrochloric acid at STP? Okay, well, that's important. We know we're at STP. What volume of hydrogen gas is released? Okay, so we're looking for a volume of a gas, volume of this. So this is what we're trying to solve. What's the volume? When 8.25 grams of magnesium reacts with excess hydrochloric acid. So this is going to be our A, and this volume over here is going to be our B. Okay, we're starting with grams of A, and we're moving to volume of B, and we know we're at STP. So if we looked at the map, sorry, it's too big to put on every slide. We start with grams of A, and we're ending with volume of B. And we're doing this volume, not this one because we're at STP, right? And so it's a lot easier just to go convert that way. So grams will be converted to moles of A, moles of A will be converted to moles of B, and moles of B will be converted to volume of B using the 22.4 liters per mole. Okay, let's walk through that one again. So we take grams and we convert with the molar mass to moles of A. Again, magnesium is going to be our A, water is our B. So we have grams of A, and then we convert to moles of A using the molar mass. Then we convert to moles of B using the mole-to-mole ratio. And then we can convert to volume of B using 22.4 liters per mole to pop out the the volume of the hydrogen gas. So hopefully that's pretty straightforward and making sense for you. If not, please jump in on office hours or email me, and we can walk through it. Okay. All right, go ahead and try another quiz. It's good to practice this stuff. Okay. Question says, what volume of CO2 gas is released when 2.0 liters of ethane is burned at 35 degrees Celsius and 0.85 atmospheres? Okay, so this is kind of just asking what the steps would be, right? So we're looking for volume of CO2. So the volume here is going to be what we want. And we're starting with 2 liters of ethane. So we're starting with volume of A. And this is volume of a gas. And it gives you the different temperature and pressure. Okay, volume of A to volume of B is what we're doing, right? So we looked at the map. We'll be converting from, it's not at standard temperature and pressure, so we're going from volume of A to volume of B, okay? So you use ideal gas law to get to moles, the mole ratio to get to moles of B, and the ideal gas law to get back down to the volume of B, okay? Let's look at our answer choices again. Okay, so we're converting to moles, right? Moles of A, then we convert over to moles of B, and then we convert to volume using the ideal gas law. We can't use 22.4 liters per mole because we're at standard temperature and pressure, okay? Okay, here it is. Oh, sorry. Oh, sorry, I messed this up. Okay. All right, let me back up a second. I got a little ahead of myself. So B would work, okay? B would definitely work to solve this problem. So if you want to just not worry about what I'm about to say, and you said, okay, I got that, what he was saying, just move on and you'll be fine. D also works, okay? Sorry. One-step conversion factor. So if you remember in the map, okay, let's go back. Okay. So we're going from volume of A over to volume of B, right? Again, I said we're going to use this pathway, convert over to moles of B, and then back down to volume of B. Okay. So what we talked about before is the part I need to add into this equation is there's a shortcut between volume of A and volume of B under certain conditions, right? That's if the pressure and temperature are constant. Because under those conditions, Avogadro's law works, okay? And if Avogadro's law works, then you can instead, you can use mole ratios as volume ratios, right? You could rearrange this here to look like V1 over V2 equals N1 over N2, okay? So your volume ratio can be equal to your molar ratio in this case, okay? I can't remember if I said it has to be at STP. If I did, I think I was just confusing the constant pressure and temperature here. But the reaction doesn't have to be at standard temperature and pressure to use this shortcut, but it does have to have a constant pressure and constant temperature, okay? So if it does have a constant pressure and constant temperature, then you can use the mole ratio as a volume ratio. Okay, so let's go back to that question. Okay, so the question is saying it's burned at this temperature and that pressure. And it's not really changing temperature and pressure, so we can assume that those are constant. Pressure and temperature are constant. So this is a one-step conversion. So instead of using the mole to mole ratio, we can use a volume to volume ratio, which is going to be equal to the mole to mole ratio. So 2 liters of ethane produce 4 liters of carbon dioxide, right? Or 2 moles produce 4 moles. If temperature and pressure are constant, you can use that. If you're just curious, you could go ahead and try the other pathway using the long way, I guess, if you will, using 3 conversion factors versus 1. And this is going to work for you, okay? Again, when I took the class, you know, I don't know, a long time ago, what was that, like 2014 probably? I never really liked any of these shortcuts. I thought they were confusing because you learn this way that just like bulletproof that works every time, right? That's this way. And then, you know, there's like, if this and this and this are true, you can do this shortcut, right? And the time it took me to memorize all the shortcuts, right, would be a lot more time than if I just used the bulletproof method all the time. So anyway, it's up to you. It's kind of like, I don't know, a real life example might be like driving like a Toyota, right? Toyotas are super reliable, bulletproof for the most part. But they're not high on, you know, new tech and fancy features all that often, right? The Toyota Tacoma gets like the worst gas mileage out of all the small size trucks. And they don't really care because it works really good. They're just going to keep doing it. And that's how I view it. The shortcuts, I think, are more like, you know, like the Chevy Colorados trying out the new diesel engines and all these different things. And they might work, you know, in certain cases. And anyway, maybe that's a bad analogy, but do what you want there. Okay. All right. So let's look at this kind of a different scenario where we're talking about mixtures of gases, okay? So if we have 17 grams of hydrogen peroxide in a closed container, what is the total pressure of the products if the temperature is 25 degrees Celsius? So far we've looked at total pressures and we haven't really thought about pressures of individual gases yet. So we're going to talk about that. So you have this reaction where hydrogen peroxide decomposes into water and oxygen and heat, okay? So the question is asking, what is the total pressure of the products if the temperature is 25 degrees Celsius? Okay, total pressure in a container is going to equal the sum of the partial pressures of each type of gas. So this is what's known as Dalton's law. So when we refer to total pressure, for example, atmospheric pressure, right? So if you're at sea level, you're surrounded by 1 atmospheric pressure. Well, the 1 atmospheric pressure is a sum of all the pressures of each individual gas. So you have oxygen in the air, you have nitrogen in the air. That makes up a lot of it, but then you also have other gases, carbon dioxide and different things. And so the total pressure is going to equal the sum of all of those partial pressures. Okay, and then a partial pressure, just to like work on a vocabulary here, is the pressure that a gas would have if it were by itself in a container. Let me see if I have, oh yeah, here's an example, okay? So air, okay, we're just talking about air. Let's say this container, we have a jar that's full of air from just the air, okay? All right, so you have nitrogen particles exerting a certain force on the walls of this jar, okay? You also might have some oxygen molecules that are exerting a certain force on the outside of the jar. And you might have some helium and some carbon dioxide, right? All these different ones. The pressure of the helium by itself is going to equal a certain amount, right? There's a certain amount of force that this helium pushes on against the total area. And there's a certain amount of force that the nitrogen exerts on the walls over a total amount of area. And then we would say what you measure, if you put a pressure gauge in here, would actually be the pressure of all of these added together. And it's really a simple concept. I think I'm like overcomplicating it in my explanation here. But your total pressure is going to equal the sum of the pressures of each individual gas. That's all we're getting at here. Okay. Oh, sorry. Yeah, so that's what we're getting at. Before we get there, this is N, sorry. So the number of moles total is going to equal the number of moles of each individual gas, right? So if you have 10 moles, you might have 3 moles of nitrogen, 2 moles of oxygen, whatever, adding up to 10. So then if we use the ideal gas law, rearranging the ideal gas law, you can have P equals nRT over V, right? So if our N is a sum of all the individual gas particles, we could split that fraction up and then find that, again, P equals nRT over V. So the total pressure is going to be equal to the pressure of each gas individually. This is the derivation. Don't worry about it. This is what you need to know. Is that the total pressure is the sum of each of the individual partial pressures given by each gas. Okay. All right. Okay. So now we talk about mole fractions. Mole fraction is kind of what it sounds like. So a fraction is always a part of something divided by the whole of it, right? So if you want to know what the mole fraction, which is usually denoted by X, the mole fraction of N is, or sorry, nitrogen, it's going to be the number of moles of nitrogen divided by the total number of moles of whatever's in the container or sample or whatever, okay? So our pressure, another way that we can kind of rearrange Dalton's law is to say that the pressure of nitrogen is going to equal to the total pressure times the number of moles. And I won't really go into the derivation on this, but I mean, we can. Don't worry about it too much. If you're interested, it's down here. But just as kind of like think about it intuitively, let's say you have half oxygen and half nitrogen in a container, right? The total pressure, or sorry, the pressure of oxygen is just going to be half of the total pressure, right? And that's basically what you can see here. So, or let's say we have just oxygen and nitrogen in a certain container. The pressure of nitrogen is going to be, if these are in equal amounts, right? We have 1/2 oxygen, right? So let's say there's a total of 10 moles. Okay, well, we have 5 moles of oxygen and 5 of nitrogen. So the mole fraction of nitrogen would be 5/10, which is 1/2. So half of the total pressure is going to be the pressure for nitrogen in the container. Anyway, hopefully that's pretty intuitive, and if you're interested, the derivation's down here. Okay, all right. So in this problem, we're given the mole fraction of oxygen in the air, which is 21%. Okay, again, this is how you denote mole fraction, is with an X. What is the partial pressure of oxygen at sea level? So again, we know that the total, or sorry, the pressure of oxygen is going to equal to the total pressure times the mole fraction of oxygen. So it's going to be 1 times 0.21, basically. Okay. So the partial pressure of oxygen is just 0.21 atmospheres, which makes sense because out of 1 atmosphere, oxygen makes up 21% of it. So what is the partial pressure of oxygen in a container of air pressurized to 3 atmospheres? Well, now our pressure changes. So our total pressure is 3 instead of 1, but the mole fraction is the same. And so we can solve for the partial pressure of oxygen in a container. Okay, go ahead and pause it and try this question, see how you're doing with it. Okay, so this should be really similar to the last 2 examples we did. So again, we have the total pressure times the mole fraction of oxygen is going to equal the partial pressure of oxygen. So our total pressure is 0.7 atmospheres, and our mole fraction is 21%. Again, that percentage should be written as a decimal when you're doing this calculation. And that tells us that oxygen in Provo gives 0.15 atmospheres of pressure. Okay. So let's look at this problem that we had that we couldn't really solve initially, and we're going to try it now. Okay, so we have 17 grams of hydrogen peroxide in a closed container. What is the total pressure of the products if the temperature is 25 degrees Celsius? Okay, so if we can solve for the products, right, we have a gas, two gases, oxygen and water. And so if we can solve for the pressure of each of these individually, we could solve for the pressure total that they give off, right? So we're going to start with 17 grams of hydrogen peroxide. We convert from grams of peroxide to moles of peroxide using the molar mass. Then we can convert from moles of peroxide over to moles of water, okay? I'm not going to go all the way back to the map, but follow this on the map, okay? So here's grams of A. You have the map written out. We're going to convert to moles of A using the molar mass. We're going to convert to moles of B using the molar ratio. And that gives us moles of water, okay? All right. Same thing here, but we use the ratio for oxygen, and that will give us the moles of oxygen. Okay, so now we have enough information to do a mole fraction, right? We also have the volume of the container, and we have the temperature of the container. So if we look at PV equals nRT, all right, we have volume, we have temperature. We've just solved for N, and we know R, so we could solve for the pressure of the container. So we know the total number of moles now, which I think it's asking for the total pressure, right? So I'm trying to remember how the slide answers this, but there's a couple ways we can go about it. Okay, so yeah, you know the total number of moles, we can add those together, and then you can plug that in for N, solve, you know V, you know T, you know R, and you can solve for P, basically, what we can do now. Another way you could do it, which would have been the longer way, is find the pressure given off by water and find the pressure given off by oxygen using PV equals nRT, and then add that together, but this would be the easier way to go about it. Okay, but if this is what you were thinking you would do, initially I thought that's what we needed to do when I saw this question, so if I solved it that way, it would have been fine, but anyway, a couple ways to do these problems. All right, go ahead and pause the video and try this one on your own. Okay, so it says we can decompose water through a process called electrolysis. So water can be converted to hydrogen gas and oxygen gas. If we decompose 36 grams of water, what will the total pressure of gas be in a 10-liter container? Oh, sorry, at 25 degrees Celsius. Okay, so we are starting with 36 grams of water. What will the total pressure of the gas be in a 10-liter container? Okay, so again, this problem should be pretty similar. We can convert from grams of water over to moles of hydrogen and moles of oxygen. We can add the number of moles together and get the total moles. Once we have total moles, we can figure out pressure using the ideal gas law. Okay. So we convert over to moles of hydrogen gas, and this is just the same as the last example, so I'm going to go a little quicker through it. We can convert to moles of oxygen, add those together, then use the ideal gas law to convert from moles to pressure. Okay. All right. Hopefully that gave you a decent idea of partial pressures. Sorry, I feel like I talked a lot about it and made it sound more complicated than it is, but it's just the sum of all the pressures in a container. And then also about mole fractions. Hopefully, make sure you can figure out the mole fraction of something and then use that to calculate the pressure
if you were given the total pressure. I think that should give a decent basis for doing the homework and practicing those ideas. So I will put together the exam review and then post that shortly as well, and get that ready for our test, which is next Monday, which is what day is that? The 20th. Starts the 20th and then it closes the 21st, right? So it's open Monday and Tuesday again, like last time. All right, sounds good. See you later.